Alright, now we want to look at the 1985 problem where we're dealing with solubility products. And so we're going to be looking at normal room temperature, 25 degrees Celsius, at two different compounds, strontium sulfate and strontium fluoride, and they're going to ask us several questions about them. First thing they want to know is the molar solubility of strontium sulfate in pure water. Well, they tell me that KSP for strontium sulfate in pure water is 7.6 times 10 to the minus 7th. And I also know that the expression for this, based on the fact that strontium sulfate, when it dissociates, becomes strontium 2 plus and sulfate 2 minus, that the KSP for this is the concentration of strontium times the concentration of sulfate. And I also know that either one of these will be in a 1-to-1 molar ratio with the strontium sulfate, so solving for either of these concentrations would tell me the molar solubility. Well, I'm going to designate each of these as S, so the concentration of strontium equals the concentration of sulfate, which would be S according to me. And so subbing into my KSP equation, 7.6 times 10 to the minus 7th equals S times S, or S squared, such that the solubility then is going to be 8.7 times 10 to the minus 4 moles per liter. So that would be the molar solubility of strontium sulfate at that temperature. Part B wants to know about strontium fluoride, wants to know the same thing. And so in this case, my dissociation would look like this. SrF2 would dissociate to form strontium 2 plus and 2 fluoride ions. And so when writing a KSP for this, we have to take a little bit different approach. It's still going to be the concentration of strontium, which hasn't changed, but when I do the fluorides, they're going to be squared. And that is going to equal 7.9 times 10 to the minus 10th. In this case, I'm going to define the concentration of strontium plus 2 as S, because it is in a 1-to-1 ratio with the strontium fluoride solid and will represent the molar solubility. That means the concentration of F minus will equal 2S, twice as much because of the coefficients. So now I'm going to sub into my equation. 7.9 times 10 to the minus 10th is equal to the concentration of strontium, or S, times the concentration of fluoride, or 2S, squared. And so this will give me a grand total of 4S cubed. If I can write a cubed. And so now we want to solve for the S. And if we break this down and do the algebra, then S is equal to 5.8 times 10 to the minus 4 molar solubility for the strontium fluoride. So it is a lesser value than the strontium sulfate we saw in the previous equation. Alright, part C starts to get a little more involved. Essentially, I've got some amount of fluoride and some amount of sulfate in a solution, and I'm going to start adding strontium nitrate. We know about nitrate is that nitrate's soluble and won't cause any problems with what we're doing. But the strontium is going to react with the fluoride and the sulfate and eventually produce insoluble compounds based on what we saw just a second ago. So they want to know which precipitate forms first. Well, we know a good rule of thumb is to look at their KSPs, so I'm going to predict that strontium fluoride will precipitate first based on its KSP. But it's not enough to predict it. We're going to have to prove it. And so we're going to solve for the concentration of each one when precipitation begins. So for part 1, we are going to say that the strontium sulfate precipitates when the following is true. I can use my KSP to figure this out. My KSP for strontium sulfate is 7.6 times 10 to the minus 7th. I know that must equal the concentration of strontium 2 plus times the concentration of fluoride. Well, I already have fluoride floating around in my system, so I have a common ion problem going on here. Oops, we're doing sulfate, sorry. So I'm going to look at my sulfate concentration, which is 0 0.1 moles per liter, since we are in a 1 liter flask. And so the concentration of strontium plus 2 in the solution when strontium sulfate begins to precipitate then is 7.6 times 10 to the minus 6th molar. We can also see when the strontium fluoride will precipitate using the similar idea. So SRF2 will precipitate when the following is true. Its KSP, 7.9 times 10 to the minus 10, must equal the concentration of strontium plus 2 times the concentration of fluoride given to me at the top, so 0.02 molar, and that is going to be squared. So now solving for SR2 plus using your calculator should give you a strontium concentration of, oops, that's where the 7 point, oh, sorry, wrong one. That's the 2 times 10 to the minus 6th molar when we punch that through a calculator. And so, looking at these two, which one precipitates first? Well, strontium 2 plus has to reach 7.6 times 10 to the minus 6th molar for sulfate, and only 2 times 10 to the minus 6th molar for the strontium fluoride. And so, which of those salts precipitates first? SRF2 precipitates first. Because less SR2 plus is needed for that to precipitate. Okay, so SRF2 does. Alright, now they want to know what is the concentration of strontium SR2 plus when the solution first precipitate begins to form. Well, look at us. We've already figured this out. That's this part right here. And so that is going to be 2 times 10 to the minus 6th molar when first precipitate forms. And so we answered part C1 and C2 kind of at the same time. Alright, moving on, part D says that as we continue to add strontium nitrate, eventually we get the second precipitate, which would be our strontium sulfate, to form. At that stage, what is the percent of the anion from the first precipitate? Well, the anion from the first precipitate means fluorine. So percent of fluorine remaining when SRSO4 forms is what? That's my question. So first I need to see what the strontium concentration is when SR starts to form. Well, I already know that. I'm going to carry that over from right here. We know from the previous question that once we hit 7.6 times 10 to the minus 6, we'll start to form strontium sulfate. So we're going to say 7.6 times 10 to the minus 6th molar will cause SRSO4 to form. And that's concentration of SR plus 2. And that's from part C. Okay, so at that point, we can go into our KSP for strontium fluoride. Remind us what that is. KSP for strontium fluoride says SR plus 2 times F minus squared. And we now know this value goes right here, because that's what the concentration of strontium will be when that starts to form. KSP value, again, is given at the top. So when we are using a KSP of 7.9 times 10 to the minus 10, and we have a strontium concentration of 7.6 times 10 to the minus 6th, we can find what F minus is by doing a little algebra. So we're going to solve for F minus, and the concentration of F minus under those conditions is going to be 0.01 molar. And so if we're in 1 liter of solution, that means that I initially had 2 times 10 to the minus 2 moles of F minus. I now have, when strontium fluoride begins to precipitate, 1 times 10 to the minus 2 moles of F minus. And I want that expressed as a percentage, and so I'm just going to multiply that by 100, and that is about 50% of the F minus remains when SrSO4 begins to form. And so, there we have it. That's all it takes to answer the question from 1985.